Okay, welcome everybody. I'd like to say thank you first for connecting to this IMechE webinar entitled Local Hybrid CHP and Distributed Energy Systems. My name is Paul Smith. I'm the chair of the IMechE Pressure Systems Group, which has organised this lecture today. The Pressure Systems Group is one of the technical groups within the IMechE, and our remit is knowledge transfer of all aspects of pressure systems among the engineering community. If you're interested in getting involved in Pressure Systems Group, please do have a look at our websites on the IMechE pages and also our LinkedIn page and get in touch that way. This online lecture today will explore the opportunities for decarbonising electrical grid infrastructure and optimising demand to drive the energy system towards net zero emissions. And coming from my perspective as chair of Pressure Systems Group, one of the objectives of today is to see how pressure systems can contribute to this. Before I go ahead and introduce the speaker, I'd like to outline the agenda for this online lecture. We're going to have around about 30 minutes of presentation material, of slides, followed by a questions and answers session. So I would invite you to, during the presentation, use the Ask the Question function in the text box and send your questions in. And then as facilitator, I will then filter them and put them to the presenter for the day. Which brings me nicely on to introducing the speaker, John Counsell. So we're very lucky to have John with us today to present this lecture. So John Counsell is a systems design and control engineer. He started his career as a rocket autopilot designer with British Aerospace in 1988. Following his doctorate, he was appointed the director of Lancaster University's Engineering Design Centre, pioneering the use of knowledge management and simulation software tools. He was then appointed Professor of Energy Utilisation at the University of Strathclyde, where he pioneered and patented the use of power distribution and battery storage in buildings. He then was appointed to create a new department of computer science, electronics and electrical engineering at the University of Chester, and he's now been appointed to direct the department's research as Professor of Digital and Intelligent Control of Energy Systems. His current projects involve design, control and simulation of complex multi-vector energy systems with industrial collaborators such as Arup, EDF Energy and Fujitsu. So in that regard, John is ideally placed to give this lecture today, and I'm sure you're as excited as me to hear what he has to say on the topic of CHP, combined heat and power, and from my perspective, where the pressure systems element fits in to that. So on that note, I'd like to hand over now to John. He has control of the slides, and John will then deliver this online lunchtime lecture on the topic of combined heat and power. So over to you, John. Thank you very much. We'll have about 35 minutes of presentation. Thank you.
Thank you very much, Paul. Good afternoon just to the audience. Thank you very much for giving me your time to listen to us today. I'm long history with the IMechE. I've developed a new department in computer science, electronics and electrical engineering, but I'm actually trained as a mechanical engineer originally. So I'm one of those people who finds themselves interdisciplinary, going from mechanical to electrical to software, and that is unlikely to change for many engineers for many years to come. But today I want to talk to you a bit about the history of hybrid CHP systems that we were part of pioneering sort of around about 2010 to 2012, and some of the projects I've done and where I see it going in the future. I think that is perhaps what everybody really wants to know, is what is the future, what could be a future for distributed energy. I don't know how many of the audience are interested in smart grids, but there's a lot of parallels between hybrid CHP, distributed energy and smart grids. I'll refer to them in the presentation as private wire networks, It is my belief that we will see the introduction of intelligence and smarter grids more on the private wire networks than on the national central infrastructure in the near future. And in fact, there's some examples I will mention throughout my presentation that show that it is already happening. So I'll go on to my content. So first thing. So I'm going to introduce CHP and hybrid CHP, what the differences really are from my perspective, and the need for hybrid CHP in our energy mix today, and particular the opportunity that hydrogen will bring to the hybrid CHP market. I just want to share with you some of the design principles that I developed throughout our research the last 10 years in this area, and some principles that are very important, and obviously some great challenges. There are always challenges when you try to create a revolution of this magnitude. There is also a very important and challenging area related to the relationship between distributed energy systems and the national grid infrastructure. And for a while now, people have referred to the interface between distributed energy and centralized infrastructure as the edge. I'm a U2 fan myself, so I particularly like that. So edge is where the interface between the grid and the distributed energy system comes together. And that is where I think a lot of the research and development is now taking place, and even companies such as ABB actually have a technology and products which are focused in this area of challenge. So how do we interface the distributed energy systems with the national grid infrastructure so that they are not so much seen as a competitor, but they are seen as a national grid resource, just like any generator of electricity, be it nuclear, combined cycle gas turbines, wind farm, PV farm, hydro, whichever. They're all just resources for the grid infrastructure. So the next part, I'm going to talk about my CHPV study, combined heat and power with photovoltaics that we did between 2013 and 2017. And some of these principles are now in practice. And I'm now looking to move it to the next stage. I want to talk to you about carbon emission considerations in all this because, that's probably the single biggest driver of the energy business at the moment is how do we deal with the carbon challenge. But we mustn't forget, the trilemma that, we're trying to get carbon emissions down, but we have to consider the cost of energy, the impact that has on residents in buildings, businesses, and industrial manufacturing. Expensive energy is not a good thing for the economy, and therefore we have to try to get a balance. And also the other trilemma aspect is the impact on national infrastructure expenditure. Billions and billions of pounds going into green energy infrastructure subsidised by the government has always been difficult to justify, and justifying it at these times during a global pandemic must be increasingly difficult. So I want to talk about that because I think we need to see the bigger picture of carbon. And then I want to talk about what I see as a great bright future CHPV with a green H for the hydrogen is what I'm currently working on, and hope to develop some projects in that area in the near future. So first of all, some of you may not be that familiar with CHP. You may be seeing this subject for the first time. So the primary thing that we have with combined heat and power is all about energy efficiency. That's the motivation of combined heat and power. And that's simply that if we were to put a primary fuel, for example, natural gas, into a generator, typically 60% of the energy is lost. That could be in the generation itself, on a combination of the distribution of the electricity that is moved from a central point to a local point. There's a lot of wires and a lot of copper that electricity has to go through, transformers and the like. And generally speaking, even a combined cycle gas turbine, you're looking at 45% efficiency for that generator, taking into account the distribution system. Whereas if you could generate locally, which means that you don't have those transmission losses, and you take that fuel in and you have your generator local and it produces heat and power, you don't have to lose the heat. And up to now, with the state-of-the-art Gembacher engines, natural gas engines, we're achieving system efficiencies, heat and power, over 40%, 40% of it in heat and power. Overall system efficiency is over 80%, and in ideal conditions, it can be 85%. On average, in practice, engine efficiencies run somewhere between 80 and 85% efficient, which I think everybody would have to agree is rather more efficient than a gas-fired generator on the national grid. And that is a huge motivator for end users and the nation, and in particular for our carbon emissions. That is all about generating electricity and generating heat. And the problem is that's only part of the equation. There's another efficiency, and that is how well you utilize it. So there's very little point in making electricity generation 50% more efficient if you're then going to power an incandescent light bulb which got the efficiency of 2%. If you used it to power an LED light bulb at over 90%, then you can see that the combined mix of utilization and generation is highly important. And that's why I'm particularly in favor of an increase of responsibility onto end users to generate their own power, because instead of being detached from the efficiency of the generator, the end user will take a combined interest on how they generate it and how they use it. One of the greatest problems for CHP is waste heat. And waste heat comes from the engine itself, which could be up to 20%. But also, it's enormous in poor utilization. So, for example, putting a CHP engine in an application where there's no need for heat would mean that you might generate that heat efficiently, but you'll lose it all because you've got no use for it. So we have to move to a hybrid CHP system where we can mix it with other generators such as PV, wind, and possibly biomass heat to be able to optimize our utilization efficiency and integrate it fully with our generation system so that the both are fully, totally operating to the benefit of each other. Unfortunately, the national grid approach is very complicated to fully integrate the supply and demand side of energy. And having pioneered demand side response in the 1990s with storage heating, I can tell you sadly that 30 years later, progress in that area with the national grid is slow. It has happened for improving frequency response, but for end users, commercial buildings, domestic buildings, demand side response applications are still relatively a niche market. At the local level with CHP, it just becomes the norm. So the need for hydrogen is very, very important. First of all, we need to improve our CHP systems efficiency in the utilisation of heat. And one of the ways we can do that is introducing renewable electricity, typically photovoltaics, which are coming down in price significantly, so that we can actually use the PV generation in the summer, and that will allow us to reduce the amount of gas usage in the summer to generate electricity. So by blending PV with the CHP, we can massively increase the CHP system's utilisation efficiency to get close to the 82 to 85% system efficiency. And at the same time, we can introduce a new vector of carbon-free electricity from PV. So CHPV, as I call it, would appear to me to be a marriage made upstairs, and we should be using it as a normal way in the UK. To reduce carbon emissions of CHP, typically the heat could be, and electricity could be 0.22 kilograms per kilowatt hour, taking into account systems efficiency. But we already know that there are plans for introducing 20% hydrogen into the natural gas flow from the pipes. So the gas source itself is going to reduce in carbon with a hydrogen injection. It's generally considered that 20% hydrogen in the grid is likely to be at the acceptable level and not likely to get much greater than that. But if we can do more to generate hydrogen locally, then we could be able to change the Jenbacher engine, which started out being a diesel engine, is now a natural gas and LPG engine, and in the future it could be 50% hydrogen engine, and let's hope so. And the CHPV system will start to move closer and closer to a net zero carbon distributed energy system. And finally, we need to move into smartness and our edge interface. Our edge interface is very important for managing the grid and how the grid can help the distributed energy system, and more importantly, how the distributed energy system in the future can help the grid. This could happen through distribution system operators or the DSO network. And what we could do is start to bring on combined cycle gas turbines only when needed. I've estimated that's about a minimum of 5 gigawatts on the grid. The rest of it could be done by distributed CHP, which would respond into demand to the grid's needs. And instead of providing grid electricity at 45% efficient, it could be doing it at 80 plus. I think you'd all agree if we replace those combined cycle gas turbines, which typically get up to 30 gigawatts plus on the grid in December and January and February, with at least 25 gigawatts of 80% efficient generation, this would be a step in the right direction. So what is the CHPV scheme that I keep talking about? Well, the first scheme that we came up with back in 2012-13 was to look at a CHP engine that was also backed up by the national grid, and the CHP engine would provide heat to a heat network, which is in the red box is the heat network, which supplied heat to buildings through heat exchangers, which would then be thermostatically controlled for the building and its zones. The building itself could have some local PV connected to the private wire network, which is in blue. And so the PV injects power onto the private wire network, as does the CHP engine and as does the national grid. We needed some form of energy storage, and we initially looked at batteries. It makes sense. Let's have a look at storing electricity. However, heat storage is much cheaper than electrical storage. Electrical storage is now retailing at something like £700 to £800 a kilowatt hour, and thermal storage is retailing at £50 a kilowatt hour. So heat storage is much more cost effective. It's also very useful for the CHP engine in improving its heat utilisation efficiency. So we chose heat storage, and in this particular case, that was a very large hot water tank. If any of you have been to Birmingham University, I believe that Birmingham University has got a couple of very large tanks, which will please the vessel people, which they can store hot water in for their CHP system. And then finally, we got a controller, the big black box, as often called, the brain, and that's got to manage this heat storage, the CHP engine control, when to draw from the grid, and it's got to manage the heat network and the private wire network simultaneously. They're both cross-coupled and interactive, and as Paul mentioned, my aerospace background, my multivariable control expertise certainly comes into play here in understanding the coupling between heat and power. One very important point is that it's very economically damaging to size your CHP engine to be the full capacity of electricity that you need, or the full heat capacity. So you need the national grid for peak demand times for sure, and you also need the gas boiler to be available for when there isn't sufficient heat available from either the thermal store or the CHP engine, or combined. So we've got some very important principles relating to the controller design that I've worked on over the last 10 years. And importantly, what we need to do is understand that what we're trying to do in a control system is effectively invert the dynamics of the system. What we're trying to do is work out how we could control the thermal store and the CHP engine to achieve an ideal grid power set point, how much power we draw from the grid, and whilst maintaining thermal comfort in the buildings. So therefore we need to create a controller, which if the process is G, we need to do G to the -1. We need to invert it so that we can tell the controller what the target building zone temperatures are, what the target grid power is, and it dynamically will tell us what the thermal store and the CHP engine should be doing to achieve it. And that's very important. Now, how do you design that controller? And that's what we discovered in our project, was that the first thing we needed to do to design the controller was to develop a dynamic model. Perhaps something you may have heard people talk about energy twins. we developed an energy dynamic twin, minute by minute heat and power, so that we could actually design the controller virtually before trying it out on the system. What we also need to do is use that model to work out how to size components in the system. You can't size these systems statically and optimize them. So you do need a dynamic model in order to be able to optimize the sizing of such a complex energy system. In the project, we looked at 3 case studies. The first one was a project, and it's a bit of a historical photograph now because sadly the building was demolished. But it was demolished because during the renovation they discovered lots of asbestos, and sadly the building had to go. Originally we were talking about retrofitting it with a CHPV system for Liverpool John Moores University to use. It was originally the post office sorting office, Copperas Hill in Liverpool. The next one we looked at was a new project, a student village for University of Liverpool. It was a residential one. This has been built and it has actually got its own local energy system, and a fantastic team the University of Liverpool has got, headed by Peter Birch and his team, do a fabulous job. If you've never been to see the local energy system and CHP system at the University of Liverpool, I strongly recommend it. And then finally, another perhaps more significant distributed energy system, if you did not know, Media City is a distributed energy system powered by CHP with a heat and cooling network, and it is run by what was then Peel Utilities, is run by Leap Utilities, and is all managed on a daily basis by them. So we looked at 3 case studies, and we built dynamic models for all 3 distributed energy systems and digital twins, and then we started to do some results. So these are examples of what we get from our dynamic simulation software called Power River, and the blue line between 290 and 295 Kelvin is the set point across the whole year from January to December. And just running the CHP engine with the energy store, the temperatures are shown in red, and the green line is the outside temperature. And you'll see in the cold months, January, February and December particularly, there are times when we don't reach comfort temperature and there's insufficient heat from the CHP engine, and it needed to be topped up with a gas boiler. But how do we size that? Well, we could use the dynamic simulation to optimize the size of the gas boiler to meet the comfort. We also, what affected the sizing, surprisingly, a little bit, was actually the electricity cooling demand needed to make sure that the commercial buildings, particularly the BBC buildings at Media City, didn't overheat. So that's the power of the dynamic simulation to get your sizing right and to achieve your ideal control response. One other thing we noticed was that heat from CHP isn't very powerful. It's a bit like a heat pump. You know, you just can't turn on 35 kilowatts of heat. So we had to introduce optimum start into the heat network to make sure that the temperatures, and this is zoomed in over a 6-day period, showing how we needed to bring the building up to temperature to prevent us not getting the ideal comfort in the buildings. Another aspect of the multivariable control is we could set a set point for the national grid. And the way we can do that is if we want to operate in island mode, that is, we set the grid set point to 0. That is, we don't take any power or export any power to the national grid. Then we would want a 0 power flow at the edge. Obviously, achieving 0 is impossible because the system of CHP generation has inertia, so does thermal storage, so would battery storage. But you can see here we've got pretty good results, plus or minus 20 kilowatts within typically a 3 megawatt system. That's pretty impressive. And here you can show we can do some work and say, well, what if we were going to use the distributed energy system as a source for the national grid? Well, we could trade 1 megawatt of power to give to the national grid and run our engines much more flat out. And you can see the control system still maintaining thermal comfort throughout the year. And this time, the grid set point is being tracked plus or minus 20 kilowatts at minus 1 megawatt, minus being export. 1 megawatt would be 1 megawatt of import. So the edge, we've definitely proven that edge technology and integration with the national grid with multivariable control and the use of dynamic simulation makes this more than feasible and relatively straightforward. I want to just talk about some carbon emission considerations. We hear that the grid is being decarbonised because of the injection of renewables, which of course is true. A big renewable, by the way, they treat as nuclear power. I've been in many debates about if nuclear is really meant to be a renewable. We won't start that one today. But it's definitely low carbon, near zero carbon, and just like PV and wind. And there is no doubt that the percentage of generation from zero carbon sources has increased. But I would like to point out to you that the national grid's demand has also reduced significantly since its peak in 2006. And the total, which is at the top of the yellow part of this graph, is down quite significantly, around about 20% down on figures in 2006. So it wouldn't be surprising to you that even if we'd kept the same amount of renewables that we had in 2006, the carbon intensity of the national grid would have gone down. And if you learn anything from my presentation, that demand reduction is as significant a contributor to decarbonising the grid as is the renewables. Famously in economics, the economist Jevons wrote that the more efficient a resource, the more we will use it. So I have to quote Julians Paradox that it would seem that the national grid is becoming less and less efficient because we're using it less and less. This is an old chart now, and I do apologise I didn't get time to update it, but basically the chart for the year of the dynamic carbon intensity of the grid varies quite significantly from the winter months, which is at the beginning and at the end of this chart, and the summer months, which is in the middle, around 8760 hours. Sorry, it's not got months along the bottom. But basically you can get up to a 2-to-1 variation in carbon intensity in the national grid. As we're going into the summer this year, there will be times where the national grid carbon intensity is almost zero. They will have to keep about 5 gigawatts of combined cycle gas turbines online to be able to reliably regulate 50 hertz frequency. So it will never be zero, but it will get very close. But in the winter, they still need a lot of gas. And that's why I believe distributed CHP is a fantastic resource for the national grid. So in conclusions, my feeling is that the CHP PV is a great high efficient system that provides an alternative to CCGTs, especially in the colder months. We need to manage the control system and plant sizing using dynamic simulation. But ultimately, we also need to find a way to reduce the carbon intensity of the primary fuel. So just to finally close off now, this is the new project I'm working on now, is saying how can we use hydrogen within the CHPV system. Well, the easiest thing would be to replace the natural gas supply with a hydrogen supply. Keele University, in their High Deploy project, I've done a feasibility study, a successful one, to demonstrate 20% hydrogen in the mains gas to drive their CHP engines, and that's been done. I'd like to do a CHPV case study doing the same. This can be done with industry or local energy systems, retail parks. Perhaps a good contender could be for Cheshire Oaks in Cheshire, near our university. Perhaps CHPV fired by the HyNet project from hydrogen in the Cheshire region could be on the agenda. Let's hope so. But it doesn't stop there. You know, we're going to have to use existing equipment, CHP with 20% hydrogen. I believe there's a partnership with the Adinas and with the Clark Energies who develop these Gembacher energy systems to move to an engine that can use a lot more hydrogen so that we can get the primary fuel closer and closer to net zero carbon. And this is where I think there's a great opportunity for hydrogen storage, high pressure vessels, storing hydrogen, which could be fed by a HyNet distribution network. And we could also generate hydrogen or create hydrogen on site. This is likely to be very, very exciting for industrial clusters where we may have buildings and industrial plants, and some of those industrial plants may be able to create their own hydrogen. We can store it and we can create it. And this creates a new vector. It's a vector that can remove the carbon dioxide to fire the engine and the top-up boilers. It says gas boiler there, gas being in the general sense, not the natural gas sense. And secondly, we could actually use hydrogen as an energy store, because if we can create it and then we can use it, then hydrogen becomes, that high pressure vessel becomes a battery, and we could then start to move towards reducing the need for thermal storage, because we can now start to control hydrogen storage instead. And I'll need a new controller, so hopefully that will keep me employed for another 5 years designing that one. So just finally, with that exciting note for high pressure vessels and energy storage and decarbonising CHP at a local level, I'd just like to thank you all for listening. And just to say something about my current projects, CHPV, H being the green H, hydrogen, is very much at the top of my agenda. I've got a number of student projects at the moment, and I'm currently working up a proposal to to base, possibly with some very large industrial investors. So if you're interested, please drop me a line. We're also doing a project with the University of Durham with Dr. Ziwe, and Ziwe and I are very passionate about creating an alternative to hot water tank storage, mainly because of the size of these tanks. By moving to a salt-based chemical storage, so that we can store the heat in the ground in a thermal battery, and that's a project funded by EPSA that we're working on, and we will be looking to see how that can help the CHPV with hydrogen scheme also. I think I've overrun by a couple of minutes, but over to you, Paul. Thank you very much, everyone, for listening, and I'll take a well-earned drink now. Thank you.
That's very good. And thank you, John, for delivering that excellent and very informative presentation. And I'm sure everyone who is connected online will join me in thanking you as well. So we do have time for some questions, and they've been coming in via the text function. So what I've done is put some of these in a kind of ordering, and we'll go through some of these with the remaining time that we have. So if you're ready, I'll kick off the first one here. So the question is more about the kind of macro level, and it's saying how do we envisage these distributed systems being coordinated across the country so that demand is assured to the customers and that so they do not suffer any loss of supply? So it's more about the overall coordination of this as a whole. If you've got any thoughts on that.
Certainly. It's a very good question, by the way. It's probably one of the biggest challenges. I think the first thing that's got to happen is there's got to be a change in attitude. And I think attitude is the key thing to solving problems. If mankind has the right attitude, I don't think there's anything that can stop us doing anything. The problem is, at the moment, is that the attitude of the national infrastructure is that these distributed energy systems are a pain in the arse. And that's the frankest, nicest way I can put it. And actually, it's far from it. They have to be part of the mix, just like a central generator. So the first thing we've got to do is get a change in attitude. It's not just the national grid that's a barrier. The distributed energy people are very, very wary of the national grid. And that is because of the attitude of both parties. So it's way beyond me to solve this. I think it's a political issue, and we need to solve the attitude and get governance and regulators to actually put the distributed energy people and the grid people together around the table and say, how are you going to solve this? There is absolutely no doubt that distributed energy is an incredibly reliable source of electricity. I'd like to quote Peter Birch from the University of Liverpool, and I don't know if you're listening, Peter, and if you are, then hello. But from my point of view, we have a distributed energy system at Liverpool University. And if I remember rightly from Peter's story, the ex-Vice Chancellor didn't want the headquarters building going on the local energy system because he wanted to make sure that he didn't get any outages. Well, I can tell you he's had more outages than the rest of the buildings at the University of Liverpool. So I think attitudes are old-fashioned about the reliability of distributed energy. And as we get more sophisticated and smarter grids on private wire networks, the claims of the national grid that they're more reliable, I think, are back in the 1980s. I hope that's helped the answer Sorry if I used a little bit of colourful language there, but I can't find a better way to describe it.
Well, thank you for your thoughts on the matter, and yeah, acknowledge the very descriptive terms being used. So yeah, thanks for the update there. There's another question here relating to the interface with the devices at the other end. So this is about the Internet of Things technology. So the question is there a potential for managing demand possibly using Internet of Things technology? For example, it doesn't really matter when we receive power to recharge things like electric cars, running washing machines or heating storage heaters, as long as it's all done by the time you get up in the morning and you want that device to actually work. So would it be possible to schedule that demand centrally, and would there be any benefit in smoothing out that demand, to make this kind of concept worthwhile?
Brilliant question again. Yes is the answer. I haven't done it specifically with the Internet of Things, but in the Part L building regulations for domestic premises, there is a standard called CELECT, which is all about demand-side response. And that was done, would you believe, as far back as 1995. And we use radio signals, long-wave radio signals, to communicate with the electricity meter to be able to provide incentives and disincentives for storage heaters to turn on and turn off. Perhaps more recently, when I was at Strathclyde University in partnership with BRE, we used DC power distribution to IT products and to in buildings and to lighting to manage when battery storage was used, distributed throughout the building in the appliances, using a power distribution system called Power over Ethernet. I think if I was going to be doing it all together now, then I would be talking about doing it with IoT. So the answer is the systems and system ideas and feasibilities have already been proven. I think it's a kind of technological change from long wave radio to Ethernet to wireless IoT.
Okay, thank you very much, John, for that answer to the question. We'll go for one more, like a kind of baseline question to make sure everyone's on the same page. So the question is, where can I find out more about the basics of an integrated energy system, please? So it's kind of like a scene setting context question.
Sorry, I'm laughing because I'm supposed to be the academic and I'm supposed to know the answer to that question. But it's a very, very difficult one to answer. Hello?
Is there some sort of basic guidance maybe on this, or some standards or something maybe, or some common literature?
Well, first of all, I would say that what was originally the Combined Heat and Power Association is obviously a first point of call. I think some of these more integrated smart grids and CHP standards are still emerging, and the Distributed Energy Association, I think it's now called, is starting to do some documents. So I would start with the CHPA documents and the distributed energy, but I still feel that the kind of information I think the person who's asking the question is looking for is not in a central place just yet. Okay. When you think about it, it's an electrical vector on top of a heat vector. So it doesn't sit well in the IET particularly much because it's got a lot of heat in it. And it doesn't sit particularly well at the moment with the mechanicals because it's got a lot of electricity in it. So this is an area of standards and documentation which is, I think, possibly falling between the stools, Paul.
Okay. Thank you for addressing that particular question. Let's go for one related to the relationship between hydrogen and gas. So the question is, Could hydrogen completely replace natural gas without requiring replacement of the existing gas distribution system?
My understanding is that the wide industry at the moment is of the opinion that a 2080 mix of hydrogen and gas is probably the safest and maximum level of hydrogen for the existing gas infrastructure.
Yeah.
I'm not an expert in the field. That's what I have been informed. So my feeling is that if I was going to move towards, say, I don't think we would ever have 100% CHP hydrogen engine. But let's say we could have 100% hydrogen boiler maybe. But let's say we have a 50-50 gen-back gas and hydrogen. My feeling is that 50% of hydrogen would have to be mixed locally, hence the CHPV concept.
Excellent, thank you. And I'll go for one more here about the sort of market of all this and the timescale. So I was wondering what's happening in this distributed energy market at the moment, and how long will all this take really to take off, do you think? What are the timescales for all this becoming more widespread?
Right. Well, first of all, I think the interest in we could just call them complexes, retail parks, university campuses, possibly a cluster of new build houses, flats, multi-dwelling units, as we often call them. There's an increased interest in CHP and has been, and distributed energy, and integrating renewables with them is also a growing market. One of the real reasons for this is and I come to the Jevons Paradox. And Jevons Paradox is about markets and economies. It's about our behavior and how we behave to price signals. As something becomes more and more affordable, more and more people use it. It's not rocket science, is it? The problem is that since we've introduced an increased number of renewables into the national grid, the price of electricity to the end users has been steadily increasing. And whilst people may not have really noticed that it's gone up significantly higher than inflation, during that time, the price of natural gas has dive bombed. And I've always operated in the energy systems business up to about 2007, when the price of electricity was typically 3 times that of gas, as a rule of thumb. We're currently somewhere between 4.5 and 5.5. And with the latest national grid intentions of introducing renewables, I think we can expect 6 to 7 to 1. Now, if you've got a large user of electricity and your electricity is 6 or 7 times more expensive than your gas, then you're going to be using a lot more distributed energy with gas. And Jevons Paradox is going to kick in big time, and we're going to stop using the national grid. And coming back to the very first question, distributed energy is not a threat to the national grid. Its increasing price of electricity is. And unless it changes, we will see increasing use of distributed energy, and we'll see increasing energy efficiency of electricity, and we will see a continued decline on the demand of electricity from the national grid. So I think there's a bright future for distributed energy, and the market will carry on.
Thank you very much, John. So we do have a number of other questions, but unfortunately we're reaching the end of our allocated time. So I would like to firstly thank you for answering all the questions you have done, and then to all the remaining ones, if you haven't had your question answered, you're more than welcome, obviously, to get in touch with us directly or via the IMechE Pressure Systems Group LinkedIn page. We're quite an active community online there, so we can answer your questions in that forum going forwards. So on that, I would once again like to thank John. It's been a really enlightening presentation, very informative to understand what the schemes are out there for combined heat and power, and then from my perspective, from a pressure systems point of view, you know, about the storage and the high pressure storage and distribution of the hydrogen as these schemes come online. John, it's been an excellent lunchtime lecture. You're more than welcome to come back and give us a follow-up lecture in the future. We can always organise that. I'd like to say, however, at this point, thank you very much. Appreciate you taking your time, and thank you also to everyone who's connected from all around the world, presumably, and I wish you all a good day. So thank you, and this is us. That's the end of our lunchtime lecture. Thanks. Goodbye.
Thank you.